Okay, in this video we're going to deal with something that just hasn't come up in the previous examples. It's not a huge issue, and it's pretty unlikely actually, but we just should be aware of it. And that's what happens if we have a coefficient on the thing that we're interested in, on the actual chemical that we have the amount for, that isn't 1. So in most reactions, when they're written out and we know that we're going to be doing energy with it, we'll have a coefficient of 1 on the chemical of interest. So let's say, for example, we're burning 5 grams of propane. We want to know how much energy is going to be produced. A lot of times when we're given this equation, we're going to be given an equation that has a 1 on the propane already. What that means is whatever the delta H is that's associated with that reaction, it is in a 1-to-1 ratio with the C3H8, which means when I get to the point where I'm going energy is equal to moles times delta H, I can just use the moles of C3H8 because they are in a 1-to-1 ratio with the energy, so we don't have any ratio to consider here. However, some chemical reactions can't be balanced properly. They can't be balanced without using fractions and have a 1 coefficient on any of the things. Let's take the combustion of ethane, for example. 2C2H6 plus 7O2 plus 4 and 6, CO2 and H2O. That can't be balanced without putting a 2 on the C2H6. So we don't have, in this case, a 1-to-1 ratio with the delta H. There's a couple ways we can handle this. The first and easiest thing to do is to recognize that while it's not proper to balance chemical equations with fractional coefficients, it's not really a big deal when we're doing energy calculations. So the easiest thing you can do here is recognize, since we don't have to follow that rule of fractional coefficients, we can simply take this equation and divide everything by 2. That'll leave us with C2H6 plus 7/2 O2 going to 2CO2 plus 3H2O and a delta H that is half as big as it was in the first place. 1,560 kilojoules per mole. So that works, that's easy, and then you have your 1-to-1 ratio, and you don't have to worry about it. You can simply use that amount of C2H6 to predict the energy directly, and you're done. However, you might not like this for some reason, and if you don't, we can still use the mole ratio way that we did back when we were doing stoichiometry in grade 11. So if I really want to work with C2H6 plus 7O2 going to 4CO2 plus 6H2O with a delta H of negative 3,120 kilojoules per mole, then I can do that. I just have to remember to include the mole ratio between the species and the energy when I would typically include a mole ratio. So let's go ahead and do this problem both ways, find the energy, and then we'll see that it's the same. So if I have 15 grams of ethane, that means my mass of ethane is 15 grams. My molar mass of ethane is 2 times 12 plus 6 times 1, which is 30 grams per mole. And so my moles is equal to my mass divided by my molar mass, which is 15 grams, divided by 30 grams per mole, which is equal to 0.5 moles. This is in a 2-to-1 ratio with my energy, so my moles of energy in comparison to my moles of C2H6 are in a 1-to-2 ratio. So when I go to solve for my energy, I'm going to end up dividing by 2. And then with that in hand, my energy is going to be equal to my moles of energy times my energy per mole. So 0.25 negative 3120, and I get 780 kilojoules per mole, or kilojoules, period. Negative because it's available to the environment. Okay, let's compare that to doing that same calculation, but with the reduced chemical reaction. So here, my 15 grams of methane would still turn into 0.5 moles of ethane. Now I'm in a 1-to-1 ratio, so I would say that my moles of delta H are 0.5. So my energy, which is equal to moles times delta H, would be 0.5. Note, this one is 2 times higher than it was before, times my delta H of my reduced reaction, negative 1560 kilojoules per mole. And note that this one is divided by 2 from what it used to be. So my result is the same. I've gone 2 times bigger and 2 times smaller. 780 kilojoules of energy being released. Basically what this boils down to is I can divide by 2 at this step, or I can divide by 2 before I even get started. Either way, at some point I need to divide by 2 because I do not have a 1-to-1 ratio between my amount of energy and my amount of ethane. So watch for those coefficients. If they exist, I would recommend just dividing things out. For the purposes of thermochemistry, we don't need to have whole number coefficients, so it's not that critical. That being said, if you don't want to, you can always use the mole ratio to predict.